Okay, I think we can start now.
Can start, but
Okay. Okay. So, good morning, everyone. Continuing with the online talk series by KTPI, we will be discussing gravitational waves today. Now, for those unfamiliar, KTPI is a vibrant collective of young faculty and postdocs, PhD scholars from across the globe. And the main motive is to encourage and foster research in theoretical aspects of physics, especially among the master students of Kerala. Now, our flagship initiative is the Active Research Training Project, shortly ART, which recruits a selected number of master students each year, assigning them to mentors from our KTPA team. I'm proud to say that we are currently running the third batch of the ART program, and the results so far have been quite impressive. The initiative has led to multiple high quality publications, which is a remarkable achievement, especially given the previous challenges in getting master students in Kerala to publish theoretical research during their studies. On that note, I would like to extend special congratulations to Ananya Prakash from St. Birchman College, Kottayam, and her mentor, Ranjit Thomas, for their recent publication, which is a testament to the growing research culture we are building together. Beyond the art program, KTPI also organizes schools, workshops, and talks on various topics within theoretical physics. Today, we are honored to host a talk on gravitational waves, and we are fortunate to have with us Professor Ghanashyam Date. Professor Shyam joined the Institute of Mathematical Science, IMSC Chennai, as a faculty member in 1987. He is a well-known figure in the realm of classical and quantum gravity, with a significant expertise in gravitational waves. His work also extends to black hole thermodynamics in ADS space. And he currently serves as a visiting professor at IMSC Chennai. Now, without
CMI.
further delay, right, sorry, yeah, my mistake.
That's okay.
Yeah, right. And now I encourage the participants. We will have a discussion session after the talk, a brief discussion session. And I encourage everyone to give their comments and ask questions. And I hope Professor Shyam will be happy to entertain. Now, without further delay, please join me in welcoming Professor Shyam. Over to you, sir.
Thank you very much, Feroz. Now, let me see how this thing starts.
Yeah, you might have a share. Yeah.
No, now I think it has come. Yeah. No, because the whiteboard was there, then I had to do something else. Then it showed my screens. Then I say screen, and then I came back. Okay, fine.
Okay.
So everything is visible now?
Yes.
I'm audible?
Yes, you are.
So now let me go to full screen.
Right.
Okay.
Now fine, yes.
Okay, good. Yes? Yes? Somebody is saying something?
Nothing. I think it's just a disturbance.
Yeah. Okay, fine. So let's begin. The title of my talk is Universe Review to Gravitational Waves. So the flow of the talk is going to be like this. I'll first briefly recall what is the electromagnetic view, and that will give us that basically we know what is the composition of the universe, what are the distances to which various objects are there. The basic features of our universe that we see is observational features, namely isotropy and expansion. That suggests that we need some theoretical framework, and the theoretical framework in which we try to understand these things is that of general relativity. I will not give full introduction to GR, of course, but we'll pick out some specific parts that we need for our talk. So three features are important, namely dynamic of space-time, there exist compact objects, and there are gravitational waves. I will discuss briefly what the two types of sources for the gravitational waves, namely so-called compact sources, specially compact sources, and so-called non-compact sources, which constitute the gravitational wave background. Once it is there, in order to understand what the gravitational waves are, we need to specify some background in a cosmological context. That background is Friedmann-Lemaitre, Robertson-Walker geometry, FLRW for short. I will briefly summarize it, very briefly summarize it, and say what is our current understanding in terms of the epochs, kind of anisotropies which are there, what kind of scales are involved, and so on. Then we'll come to a little closer look again back to the theoretical one, namely what kind of gravitational perturbations are there. There are many types of perturbations, but I will focus, restrict myself only to gravitational perturbations. Again, some very basic introduction to that I'll give, namely basic equations, some kind of solutions, gauges, and so on. Then I will discuss what is observable and what is the nature of perturbation. So that will be some example that we'll do. And then finally, I will come to the other parts of gravitational waves in the cosmological background. Those are detected by or looked for search from pulsar timing galaxies in the nanohertz frequencies. So that is the plan of the flow generally. So that's how we'll begin. Mostly it's going to be pedagogical in the sense I will try to explain things rather than give latest information and data and parameters, etc. My aim is to convey what kind of logic goes into the various steps involved in that. That's what I'm trying to do. Okay, so without further ado, let's proceed. So electromagnetic view. So this is simplest. All you do is look up in the sky, what you see and what we saw from centuries, planets, stars, Milky Way. We are lucky enough in open space, not in the urban areas. That is the simplest thing we can see. We just look up and see that. Okay, a little better, use telescopes. Then you start seeing structures to this. You see star clusters. You begin to see galaxies if you have bigger telescope. If you have even bigger telescope, you can see galaxy clusters of galaxies. Now let us focus on to one particular galaxy and look at through different filters. That is different parts of electromagnetic waves. So here is the view for the galaxy called M51, which is also known as the Whirlpool galaxy. So here is the view. If you look at the focus on that and filter light only in the infrared, some of these are, of course, reconstructed images. They are not visible in the eye because they are not in the visible spectrum. So this is how the infrared picture of the Whirlpool galaxy looks. Visible is what we'll see in ordinary usual large telescope. Ultraviolet, the view will look like this. Radio waves, it's very different. X-rays is even more different. And of course, there is an empty box here, which I'll comment on after some time. How will it look if it were to somehow find this quote unquote telescope, which will be using the gravitational waves for that? So what does this tell us? It tells us that whatever galaxy is there, its view, when you look through different parts, it looks different. And why is it different? Because what we are seeing is actually the sources which are producing this particular kind of radiation, that is infrared, visible, ultraviolet, etc. And what we see is the distribution of those sources. The different images say that there are different distribution sources which produce this. For example, there could be stars which are very hot, or there could be gas which is emitting, reflecting light, etc. So you'll get different features, and these different images tell us the distribution of sources. So if you were to get gravitational waves sometime, astronomy develops enough, we may get a very different view of what the galaxy looks like. For example, in X-ray, you see almost nothing except some bright spot here, and radio looks very different, and so on. So that is what the electromagnetic view from different filters shows up for a given object. Okay, let's proceed further. So now we have to find out, we have understood to some extent there are stars, galaxies, etc., etc. How far are they? That's one of the essential ingredients which goes into understanding or building our understanding of the universe. And that goes through it's an elaborate procedure with the so-called cosmological distance ladder. It goes in stages. The nearby objects you look through just triangulation and see how far are they. Then use parallaxes. Then use sort of main sequences, So you look at the population and see that, assume that the populations which are similar will have similar properties, namely the intensity. Remember, in order to find the distance, all you know is that you can measure the light intensity or whatever frequency you are measuring at Earth, and something which is emitted at the source. You do not know how much is emitted, and unless you know both of these distance, both luminosities, you cannot find the distance. So what you measure is available to us. Distance is something to be built with various theories and various methods which are there. Again, it's a very separate story in itself, how this distance ladder is built up and what goes into that. But to summarize here, here's the pictorial summary. I don't know whether you can see it. You probably can't read it. Earth is here, Sun is here, Earth is just around it. For nearby objects, we can see using the parallax method. We go a little further at galaxies, there are some types of stars called variable stars. Their luminosity and period are correlated. and that is studied separately. So you look at the stars and look at the what is the period of variability, and then you find a relation between their brightness and the variability. Empirically found this, and you say, okay, if I see similar kind of variability somewhere else in different galaxies, then it must have such and such luminosity. I know the luminosity on Earth, and therefore I know the distance. So that's the kind of logic which is used. So that is with that you can go up to about 10 power 6 parsecs. Parsecs is about 3.2 light years. Then you go to between different galaxies. So now you look at stars which suddenly become very bright or called nova, or look at the brightest star among the population in the galaxy and say, okay, brightest star in my galaxy has such and such luminosity because I know the distance independently. Similar thing must be true in the other galaxy. Again, using that to find out how far is the object, and we go up to about 10 power 7 parsecs. Galaxy clusters, you have to look at supernovae and brightest galaxies and so on. The logic is the same. You have to find some estimate about what the intrinsic luminosity would be. You know the luminosity on Earth, and therefore you infer the distance. That gives you distances up to about 10 power 10 parsecs. Remember, these are the scales at which the size of the universe is currently understood. Only about 100 years back, we didn't know that there are different galaxies exist. So you can imagine in 100 years how much our knowledge has changed. So this is how the distances are. This is how the objects are distributed at various length scales. Okay. What do we observe from this? If you look at now that you've got the objects and their distances mapped up in some way, we can say let's focus on those objects which are beyond, say, about 200 megaparsec. So we are looking at the sky and asking out all other sources which are nearby, so solar system, planets, etc. We are just going to ignore them, erase them from our screen, and only look at objects which are beyond about 200 megaparsec, and look at how it distributes, how it looks in the sky. Well, it looks pretty close to being isotropically distributed. That is, in any direction that you look, there will be roughly same number of such objects which are around. Now, this is an observed fact. And now you say that, okay, what do I do with this observed fact? So one thing is to say, okay, maybe this is, if I were to go to different galaxies, which of course I cannot, then maybe it will look the same. It's an assumption, of course. But I have to make some assumptions in order to make progress. Otherwise, I cannot write even the first step in the equation. So then one invokes the so-called cosmological principle. Namely, on sufficiently large scale, universe is spatially homogeneous and isotropic. Isotrope is something that we observe. Homogeneity is something that we extend with the assumption, the cosmological principle. This principle has a long history, and it was also pointed out by Newton, so it is as old as that. The logic again was that laws of physics, the basic properties of matter are same everywhere, and unless we make such an assumption, we have simply no way of trying to figure out what may be happening very far away, because we cannot take our laboratory there and do experiments. So this is an assumption which is necessary in order to build some picture. Without that, you simply cannot make any progress. So fine. So we have found this, make this assumption, assume that the universe is isotropic and maybe it's the same everywhere. Then Hubble happens to observe around 1939 that if you look at the light from distant galaxies, then the light appears to be redshifted. Furthermore, the redshift increases linearly with the distance to the galaxy. So further the galaxy, more is the redshift. So light coming from that, the spectral lines are shifted. You can track hydrogen or any particular element that you can find. And that's how we determine the redshift. Now, this is something, again, an observed fact. Now, if you say, one can say, okay, everybody seems to be going away from Earth. But if I now combine that with cosmological principle, they say maybe if you were to look at it from any other galaxy, it will look the same, which means all galaxies are going away from each other in some way. There is no common center from which everybody is going away. That is the idea that comes from this. So this means that the conclusion from this is that we live in a universe which is expanding everywhere. Everywhere is the assumption following from the cosmological principle. Okay. Okay, let's proceed further. Now, how do we understand this? What is the theoretical framework in which we can try to formulate what this expansion is, how do we quantify it, and how do we try to understand, explain why the expansion is there or how much it is and so on. So for that, the theory which is now of course used is the general theory of relativity, again about 100 years old now, more than 100 years old now. So what are the main points? Of course, GR is a very large subject with various features in it and so on. for us, what is important, first feature is that what we know as apple falling on earth, the Newtonian notion of gravity, the gravitational force is understood as a manifestation of third space-time geometry, which is generically dynamical, which means it is not something fixed once and for all, but depending upon distribution of matter, it will be changing, and that changing is allows us to say that the space-time geometry that we use in our observations can be changing. Now, this is a good feature because you observed that universe is expanding. So perhaps this feature is the framework is such that it can accommodate such possibility. This is one feature, qualitative feature. Secondly, GR is an extension of special relativity to gravitation. So when Einstein tried to say, okay, electromagnetism is actually implies also a special relativity, but Newtonian gravity doesn't. So I want to have a theory where such things should not be there. So Newtonian gravity should also get generalized, and that generalization gave us general theory of relativity. From special relativity, we just note that E equal to mc square, which says that energy is the equivalent of mass. So that means energy will also have inertia, and energy can also produce gravity because mass produces gravity. So that is the feature we are going to use. This is a summary or qualitative heuristic feature of that. In equations, it will turn out that when you incorporate this, the nature of gravity will tell you that gravitational interactions also produce further attraction in gravity and so on. So gravity gravitates again. So that is the notion which is there. So all forms of energy can gravitate. Now, what does that mean? The implication of that? Well, very highly compact objects can exist. For example, using only special relativity, Chandrasekhar found that there is instability among the so-called white dwarf stars. They are compact objects about 4,000 kilometer radius for a roughly solar sized mass. And in fact, we found that if such an object were to have a mass which is about 1.4 solar masses, that's the Chandrasekhar limit, then there will be instability. If you put little more mass on that, the star will simply collapse. It cannot remain stable. Such a thing would not happen in Newtonian gravity if you have stellar structure to be understood in Newtonian gravity. So GR actually gives you this further feature that if the white dwarf becomes unstable, what does it mean? It will again collapse. That means it will get even smaller. It was already 4,000 kilometer radius, it will get even smaller. Well, it can go on. There is a whole theory of how this thing proceeds. Next level where this stable star can come is so-called neutron stars. And they have again corresponding limit called the TOV limit. It's about 2.5 solar masses. That's not as clear as white dwarf limit and the Shekel limit, but that's up to about 2.5 solar masses at the ballpark figure we can take. That has a size of about 10 to 15 kilometer radius. You can imagine mass of the sun compressed into only about 15 kilometer radius. The densities become 15 grams per cc. So these are extremely compact. They're as heavy as sun, of course, I mean solar mass scale, but they're extremely small. Now, what does it mean? Once they're small, okay, this also, just to continue for a little bit, this also has its instability. If you put a little more mass into this object, the poor fellow cannot survive as a star, and it just collapses. And now, at least we do not know any other mechanism by which another stable star can exist, which is even smaller than neutron star, but has size which is larger than so-called Schwarzschild radius. So if that is the case, then the only thing that can happen, it collapses and forms a black hole. That's the intuitive notion of black hole that we have. An object whose size is smaller than its corresponding Schwarzschild radius, which is determined only by its mass, the Newton's constant, and the speed of light. And the Schwarzschild radius is 2gm by c square. So given the mass, that therefore there is a fixed value, namely Schwarzschild radius. So if the physical size of the star happens to be smaller than that, then we have got a black hole. So GR is telling us that because of the fact that gravity can gravitate again, not just mass, because gravity has energy, highly compact objects can exist. Now this means if they can exist and they are so compact, they can also come nearby. Suppose, for example, sun size is whatever 100 times size of Earth, so 600,000 kilometer radius roughly. You cannot get closer than that because you will have sun merging with the star boundary, so to say. It's not rigid, but once you go a little inside, it's no longer, it can use the same equations that you have. but the objects are compact like the white dwarf, neutrons, and so on. You can get very close to them. And that means that your Newtonian gravity is now highly modified. It can no longer be used in the same form. Okay, let us keep this aside because we need to use that in a moment. CR also predicts one more feature, namely because of the fact that gravitational effects also must propagate no faster than speed of light. The equations that tell us that there is also possibility of gravitational effect propagating at finite speed, i.e. gravitational waves. Okay? So that possibility can exist, and this is only a possibility at this level. There is this logic has to be, I mean, the waves have to be established and so on. But such a thing is there, then it can convey energy, momentum, and angular momentum, and so on. So now this means that the compact, so binary objects which are, say, compact objects such as neutron star or black holes, and they're close enough, but they can also start radiating. We'll discuss that radiation in a minute. They can start radiating, therefore lose energy and moment, which means they can start merging. How fast can they merge? Well, that depends upon how close they are. And this is where the fact that these objects are very compact comes into play and says that, okay, they can be close enough, they happen to be close enough, then they can merge fast enough so that we can observe it. That is, the rate of merger is less than the age of the universe. This thing is possible only because such objects exist. Remember, these neutron stars were not known in the 60s. So when gravitational radiation was discussed, it was said, okay, maybe it radiates energy and so on, but solar system type objects, planets, it will take much larger than the age of the universe. We'll never actually see the mergers. That was the logic which was used. Landau Lifshitz mentions that. But once the compact objects were discovered, then say, now it's a possibility. You could actually have a merging of so-called compact binary. Okay, so that is the new feature which general relativity provides us. It can accommodate expanding universe. It says that there can be compact objects and they have been discovered, and there can be possibility of merger. Is something that is also now we know after 2015. Okay.
Hi, Shyam. One question.
Sure.
So you said that these compact objects, they exist in general relativity,
Yes.
but within Newtonian gravity, could you not have like, I mean, you could have objects which collapse and form
Okay.
compact objects, right? If it is.
Yeah. Okay, so if you look at the simplest way is to look at the spherically symmetric distribution and for the stability of such an object, it is indeed the case that you can have arbitrarily high pressure, arbitrarily heavy object compressed into a star. So you can have in principle very high mass. However, then you start putting in the fact that how much is the how much pressure can be there. Pressure at central doesn't have to go to infinity, because the Newtonian stars can be stable. That's true. Okay. But then you start looking at if the size gets smaller and smaller, the object is going to be heated. And now the other processes have to take into account. They start taking, like atoms will start dissociating, electrons will come, and so on and so forth. If you now look at the corresponding so-called polytropic equations, the exponents then changes once the objects become relativistic. And it is that which says that now you have to, in fact, white dwarf thing doesn't require Einstein gravity. It's enough to have the Newtonian gravity, just polytropic changes. But when you extend it to objects which are now the electrons are also strict and you are largely neutrons, then GR is necessary, and that is what gives them stability. So it is true that strictly Newtonian theory, you can have arbitrarily size objects, but then you are ignoring various other. That is only for a spherical distribution without the temperature reflection or things taken. The polytropic equation will change if you start. So special relativity alone will tell you that equation has to change, and that introduces the instability. Do I answer your question?
So is the statement that if you look at something of the mass of the neutron star, then you do see that special relativity has to be applied, and after, because the motion becomes.
White dwarf alone will tell you. No, white dwarf alone tells you that that is the case. Yes. I mean, the objects which are close to the surface, they're in order to stay attached to it. So it's like, say, you're taking a satellite which is going around Earth, and it starts getting closer and closer to surface of Earth. Its speed increases in order to stay in that orbit. If the Earth gets even smaller, its speed has to increase further. The speed will actually become a speed of light if you go to black hole, Schwarzschild radius. But little beyond that, it will start getting relativistic. Yes.
Okay, so let me ask the question in another way. Suppose you have an object of that has a mass of a neutron star. Okay, I mean that an object that is big enough to become a neutron star. Suppose you only had Newtonian gravity. So in that case, that object. Would it collapse to a size which is larger than the neutron star, or I mean,
we'll have to check the numbers. Let me come back to it later. Remind me of again. I will come back to it later. Let me continue. I'll come back to it. And if I don't know the answer, I will answer it later. So yeah, I keep that in mind. Yes. So let me proceed. I will come back to it later. Any other question? Okay. So let's proceed. So it is important that first of all, compact objects exist. That is one thing. And they can be therefore close to each other, and therefore they can merge. Merging possibility exists because of gravitational waves. So black holes and their mergers are brand new processes which are not visible in the electromagnetic. So electromagnetically, we will not see this either black holes, or when we see them indirectly from the accretion disk and so on, but not really and when they merge. Now, when the gravitational astronomy becomes more mature, so that you can localize the mergers and the distances to them, then we can have new features in the sky map, because now we'll have the merging black holes as sources which are producing gravitation, which are not visible to electromagnetic view. And then the blank box that we showed in the beginning, I showed in the evening for M51, will now display the gravitational waves view of the M. So it will show the distribution of black holes and their mergers as opposed to other stars. Other stars are of course visible in other spectrum, electromagnetic. So that is where the gravitational waves view will change, because we'll start looking at sources which are not accessible to other means. Okay, fine. Now, such mergers and localized, we already seen the merger, so that's a reality now. 2015, when the gravitational waves were detected, and now there are about 100 such merger events have been seen. So they are real now, they're established facts. So mergers and other localized sources would have been producing gravitational waves all through the history of the universe, not just that we observe now. They would have been around, and they will still be going on, and so on and so forth. Now, they will contribute some background, which, because we do not know their distribution, so we'll have to say that they're distributed in some fashion, and we can only talk about some background effect of the waves which are there. So that is one source that can happen. There could also be primordial gravitational waves, because we also know from CMB results and so on that there could also be fluctuations the very early universe about which we know nothing about. So as a logical possibility, we can simply say, okay, we have this equation, we have the basic fields which are involving gravity, so there could be fluctuations among that, and therefore primordial gravitational waves could also exist. Again, we know nothing about it except to say as a logical possibility. So we'll say that they constitute some sort of background. So background could be because of localized sources which happen to be distributed in some fashion, or which are sources which are intrinsically not localized. Now, the famous CMBR, cosmic microwave background radiation, is the electromagnetic hum left over from the photon decoupling era. That's about 300,000 years after the Big Bang. Similar hum is expected when the neutrinos decouple, and that is supposed to happen roughly around 1 second after the Big Bang. Now, these periods are what they are because the photons will interact with the charged particles. As long as charged particles are there, photons will be doing whatever they are doing, and only if they decouple, they give the snapshot that you observe in CMBR. Likewise, when the neutrinos decouple, we'll see what was the distribution of whatever matter was there at the time of decoupling of neutrinos. Now, gravitational waves interact so weakly that essentially it doesn't interact at all, which means that's always decoupled. So if we see this hum from the very early universe, that is different from those which are produced from localized sources, then essentially we are seeing the image or information which was there from the Big Bang itself, or very, very close to Big Bang. So finding such a thing is, it's not clear how much we learn in terms of details of the Big Bang, but such a thing being discovered will also say that the fluctuations that we postulated or imagined are actually physically there. So that is an important feature that gravitational background will provide. Okay, So let's go now, take a little closer look at the compact sources and what kind of information we have. So I will, of course, summarize very, very briefly. So generally write the metric tensor, is 4-index G nu, which is considered to be flat background, so Minkowski spacetime, plus a little bit more. There is an epsilon sitting, which I'm not writing, but Hij is considered to be something which is small. So the idea is that we say, I imagine the gravitational waves as something which are minor ripples in the background spacetime, which I take to be Minkowski. That's how it was done initially. And then if that is the case, then solving the Einstein's equations at the linearized level and looking for solutions and finding out various gauge issues, etc., we can look at the space part, Hij part, that comes from, sorry, this should be T here and not R, not RR, but TR. Sorry, that's a typo which I have missed. It is obtained to be proportional to double time derivative for quantity called Qij, which is the quadruple moment of the object which is producing these waves. So which is because of which these Hij are there. So the idea is that there is some flat space time. We are having some star or some objects there, which is doing something. It has a quadruple moment. So if I take mr square, integrate over the, density times distance from the axis that you choose, calculate a quadruple moment of the mass distribution. And let's say it is changing. For example, two stars rotating about each other. It is changing, therefore that quadruple moment has a time derivative. If there's a double time derivative is non-zero, then it will produce the waves which are amplitude is given by this. And r is the distance from the source, and t is for the time, and c is the speed of light. So this is what Einstein's quadruple formula gives. The analysis of linearized Einstein's equations give us Hij of this form. Then you can also find out what is the energy loss of this quadruple moment, which is changing. That loss is proportional to the triple derivative, third derivative of the quadruple moment. Again, there are some specific projections, etc., which I am glossing over. So roughly, it means that you have to have a matter which is not exactly spherical. It should have quadruple moment which is non-zero, and that quadruple moment should be changing in time, and not just changing. With at least double derivative has to be non-zero. Otherwise, this is not there, and if it is there, then triple derivative 0 will again mean there is no energy loss. Okay, so this is what we get from there. Now, the question is, this is for Einstein did it himself almost immediately after he got his equations. That's the first thing to sort of look at, apart from the precision of perihelion, etc. The question was, because the general coordinate invariance was not that well understood. So the question was, is this what you see really real, or is it just some mathematical equation that you get and some solutions? Okay, you can always solve for differential equation, get some solution, but so what? Are they physically conveying anything? Like Maxwell's equation, you can write arbitrary solutions from the equations. Mathematician can do that, do it very smartly. But do they carry energy and momentum? So if something is produced, am I going to get a receiver here and receive it? So that is the physical part of it. And that was not very clear whether gravitational waves, as understood by Einstein in the initial stage, whether they are really physically real or not. This issue lasted for quite some time, going back and forth. They are real, they are not real, etc., etc. Finally, it was in the 50s, 57 to be precise, Bondi, and then subsequently Bondi, Pirani, Robinson, and then further collaborators, Bondi, Metzner, 62. They settled this issue, and the conclusion was the following: that Einstein's equation localized sources, that is beyond. So there is it's at t equal to some constant time. There is a distribution of matter which is bounded. So there exists a region beyond which there is no matter. So matter-free region exists. So that's what is meant by localized sources. Such sources, if you look at the equation, they do admit solutions which are radiative. That is, they will actually carry, radiative means that the solutions will fall off as no more than, not faster than 1 over r, so that you have a chance of detecting the energy loss, etc. at infinity. That's what radiative will characterize. And not only they will carry energy, but there is a corresponding loss of the source mass. So energy is actually energy which you receive at infinity, or very far away from that, is actually coming from the source. Yeah. Yeah. Is there a question? So there are two things. Not only the waves exist, so solutions for the full nonlinear equations exist. They carry energy. You can define energy appropriately, and such a you can show that it has properties of energy that you get. And the change in energy that you will get, if you detect more energy, you see that there is also notion of what is called 1D mass, that there is accompanied loss of the mass whenever the gravitational radiation is seen. This is very important because not just that energy is carried, but energy is coming from the source which is producing. So there is a conveyance of energy from source to far away from the source. Now, this established that yes, gravitational waves are real, and they can actually use, they can convey the energy momentum and angular momentum also from some localized sources to faraway places. Now, this prediction, this is the prediction, therefore. Now, its confirmation came. There are two different things. One is the so-called orbital decay of the binary pulsar, Hull stellar pulsar, which was discovered in 74 and tracked over 30 years. And I don't have the figure of this. It showed that the period of the pulsar is changing, and that is because the binary pulsar, the companions are getting closer. Once they come closer, the period gets faster. So you will see that the orbital decay, and it will fall exactly this in the how much the period accelerates. I mean changes depends upon how much energy is lost. So we say that this is a rotating body. I know calculate its quadrupole moment. I find out from the period what its time derivatives are. Find out how much energy is lost by Einstein quadrupole formula, and say if this much energy is lost, that loss must be coming from the energy, Newtonian energy that you will write for the binary system. And therefore, because that energy is less, it must shrink. And then I will find out how much is the shrinkage or how much is the loss of increase in the period as a function of time. And that exactly matches with what quadrupole formula will give. And this was what was seen, and the Nobel Prize was given in 1993. Secondly, the fact that the energy loss is associated with the energy measured at infinity also tells you this Hij, which is here, which we calculate, this should be T, of course. Then it will generate a characteristic chirp form, waveform, that is gravitational waves, because see, if it was just coming there and not affecting the source, then there is no reason for the frequency of the source to change. And the frequency of gravitational wave is twice the frequency of the source, because this quadrupole moment which is there. So unless the frequency changes, you are not going to see the waveform to be changed. So the loss of energy says that the frequency is changed, and because of the waveform changes, that waveform has a characteristic change, namely not only frequencies start getting higher and higher, periods start getting shorter and shorter, but the amplitude increases, because if this changes higher and higher, this H is proportional to that. So we are going to get increase in the amplitude. So that gives this so-called characteristic chirp form, which I can just say that it goes like that. So sorry, I don't have the. I mean, I have the image, but then it was getting more than the number of slides. So this is again something which was in fact used and discovered in, and then the Nobel Prize was given in 2017. 2015 was thing, announcement was 2016, and Nobel was given discovery of gravitational waves. Nobel was given in 2007. So these things have been theoretically attempted, theoretically well-founded, experimentally verified. Okay. This is for compact sources, where many things are well understood and they are confirmed. But there are these so-called non-compact sources. That is, sources which we cannot say that are localized, and therefore there is no region in space beyond which there is no matter. Okay. So I cannot use the equations to say I have only the vacuum equations and I will look for the solutions of that. I cannot do that because matter is always there. So that is what it means by non-compact sources. Now these sources could be coming, as I mentioned earlier, they could be producing the gravitational wave background. It has two components, either astrophysical sources, which are distributed all over, like in different galaxies, all over the mergers could be there, and therefore they will come. Or there could be primordial fluctuations. We do not know how they come, but let's assume they come. Now, in this case, because we don't have this complement of compact region where the space-time is essentially empty, matter-free, we don't have a notion of asymptotic space. We can at best talk about what happens in asymptotic future or what happened in asymptotic past. So therefore, we don't have the general analysis that we can do, but we can consider the linearization about some homogeneous background. Homogeneous because I want the distribution to be non-compact. It can be inhomogeneous, but the first approximation will take homogeneous background, and then we'll consider perturbations can be, the linearization can be non-homogeneous. So this is one feature. So our analysis method of analysis has to change. It's not going to be, of course, there are still solutions of Einstein's equation, but they are not going to be of the same nature. Secondly, since we know nothing about how the sources could be distributed or how the primordial fluctuations will come about, the only thing we can assume is there's some distribution, some randomness, which we do not know. All we can do is to characterize it in terms of correlation functions and make some assumptions over that, and then infer from observations what we want. So the only information we can hope to get is the statistical information. We don't have any other direct access. Now, to give us schematically what it comes, let's say that delta phi, yeah, delta phi as a function of time and Fourier mode k. Suppose it describe a generalized, some generic linearized perturbation. It could be because of density perturbation, because of matter perturbation, because of gravitational waves. We'll write the equations a little later. If such a thing is there, so it is produced somehow, and it is statistically distributed. What do we mean? We simply say that we assume it is such that this first moment average of this is going to be 0, but the correlation function between two modes is going to be proportional to delta cube k minus L. So unless k is equal to L, nothing is there. But delta phi square, therefore, at a given k is non-zero and is given by something object which depends upon k and maybe function of time also, because this is function of time. So this is the central quantity that we get. In principle, of course, there could be higher moments and so on. But again, it's a question of saying how many moments can we experimentally detect. The first moment being 0 can be always arranged. You simply subtract from the average and get it to be 0. Second moment is the non-trivial one. And if it happens that the
Sir, I have a question.
Yeah. Please.
Can I ask a question, sir?
Sure, please.
Sir, all the gravitational wave sources we encounter, am I clear? All the gravitational wave sources.
Say it again.
Yes, in that case, how will the distribution of the matter within the source matter? Because it can be, what I understand is that I don't know whether I'm wrong, it can be as good as a point source where the distance is so much.
Sure. Oh, yeah.
Okay.
It can be a point source, but there could be many point sources which are just as you see large scale distance, galaxy stars you see, they are point sources, right? But you see them isotropically distributed, which means the number of such sources per unit area is roughly uniform. So here also you get point sources, same just coming from astrophysical sources like mergers and so on. They are point sources, but it could be very distributed in the space in such a manner that they can be thought of as distributed everywhere. So anywhere in the sky you look at, there will be such sources. That's what I mean by saying that they are non-compact sources. Not individual sources, not non-compact. The distribution is not.
Thank you.
So that is for the astrophysical background. The primordial fluctuations are of different nature. There is no associated localized source. We simply assume that the fluctuation is there and see what happens. So there are two different cases, and I will talk a little bit more about it a little later. Is that okay?
Okay, sir. Thank you.
Yeah. So then the 2-point function. So if the distribution happens to be Gaussian, which you don't know, then this 2-point function is sufficient. If you specify this, all other moments can be, all other correlations can be calculated. So this is the basic assumption that we made, and this is the quantity of interest which will characterize our assumptions about what kind of stochastic distribution it is. Yes, that's all that we have. Okay. So this is all. This object is what is going to be our central observation that we make. Okay. So now that I mentioned, we have to consider the waves that's coming from linearization of some homogeneous background. Now to spend some time about what is the background. Okay. Am I time-wise? I'm okay. I think I may be. I will need more time. Is that okay?
Okay.
Yes.
Yeah. Okay. So right. So here is a very quick rundown, and this many of you might have already known. This is just to sort of set the stage. So what is the background? The background that we are seeing, of course, the FLRW, which is homogeneous isotropic. So the metric is taken in the form of this. This is called the synchronous time. Is the scale factor for the 3 geometry. This is Euclidean. I'm taking only the so-called spatially flat model, which is the currently favored cosmological model. And there's a corresponding stress tensor that I can have because it's homogeneous and isotropic. You can have only 2 functions, namely energy density and pressure, which are functions only of time. This is how the description of basic matter content and the geometry is. This goes into the Einstein's equations, and then the variable which is unknown is the scale factor, and of course rho of t and p of t. Only 3 variables are there. So when you plug that into Einstein's equation, you get equations can be rearranged, and they go into one is double dot equation, one is dot square equation, and one is the equation of relating the variation of density and pressure and the scale factor. This conservation equation. This stuff is this I have made it smaller because I'm just packing it and very quickly going over this. What are the solutions of this? Well, these equations by themselves are not fully determined. I need to specify what is the pressure as a function of density. That is the model I have to choose. So if we choose the pressure to be 0, which will typically correspond to saying that the distributed matter is non-relativistic in motion, so its motion can be neglected, so its pressure is 0. Then the density and the scale factor, they behave in this fashion, and the scale factor goes as t to the power 2 by 3. Cm is some constant. This is called a matter-dominated evolution. There could be relativistic particles. I mean, whatever constitution of whatever is constituting the matter is relativistic in nature. In which case, the equation of state is going to be p is equal to 1/3 rho, and then the rho and scale factor fall in that fashion, and scale factor goes as square root of 2. You could also have a situation where the cosmological constant, in which case the pressure is equal to minus rho, which is lambda times lambda over 8 pi. Lambda is taken to be positive, etc. In which case the scale factor expands exponentially. So these are the qualitative features of 3 different types of other. There is also technically something called conformal factor, which is just you write this matrix, pull out a factor of a square everywhere, replace t by eta, and then what you get is eta is related to this. The matrix becomes conformal to Minkowski matrix. That's why it's called conformal time. This becomes convenient. I'm just mentioning it because I'm going to refer to it. This just becomes convenient way of handling the equation. So important point is this eta is negative if the universe is expanding and accelerated. If it is, and it's positive if it is decelerated, it is always increases with t. So these are the only features we need to know. Here is the conclusion from these various equations which are there. And current picture of universe, again, I think I can, are you able to see it? Probably not. Reading is very difficult. So this is the Big Bang where universe is supposed to have begun. Then just shortly after that, there was an era of exponential expansion, which is called the inflation period. Then was the standard model era where the particles of standard model that we know, first was the GUT, the grand unified models. There are so many of them. So there could be particles of those. Energy scale is about 10 to 15 GeV. Then it universe expands, so it cools and cools to a era where standard model picture will be particles will be visible. Cools further, then you get nucleosynthesis. Finally, you get protons, electrons, and photons. Of course, they are interacting. They form plasma, and at some stage, because the temperatures fall down further, there are not enough electrons and photons available, and photons have been decoupled. And then the photons which decouple, they go freely until again they get marginally affected by the so-called reionization era, and that is what we see as a CMB. So CMB radiation comes from this so-called surface of loss scattering. If the neutrino background weather, it will come somewhere here. Roughly 10 seconds, so it will be just little before that, and gravitational things will be coming from here. And this is shown to be expanding because we are supposed to be living in the currently accelerated expansion. So lambda seems to be dominating, and therefore this is shown to be like this is like the picture which indicates, and this is where all the objects that we see around stars, galaxies, etc., they are produced in this era. So all this is happening after about 300,000 years after the CMB. Okay, so universe expand at a, now because universe is expanding, it expands at a certain rate, and that sets a certain length scale. It's called the Hubble radius. This is the important scale. Namely, it's inverse of the Hubble parameter. Namely, Hubble parameter is defined as a dot by a, the rate at which the scale factor changes. Inverse of that defines, I'm using the units of course equal to 1. So the time unit will go with the length unit, and this defines a so-called Hubble radius. On the other hand, there are physical sizes. So our metric, as you saw, was this. So this is the, if you use this metric to define the measures, this is called a co-moving length. And the real metric is of course a square times that, and which is time dependent. So the physical lengths are going to be changing in time. and they always change with the scale factor. So there is a Hubble radius which can be changing and order, and of course physical length always increase. This can actually either remain constant or decrease. This ratio of these two controls much of the structure formation. So depending upon how it is going, which scales are going to be relevant, which scales are not going to be relevant, is all controlled by these two. So this is the crucial fact that universe expands, controls what kind of processes can take place. Okay, now all that has so far was related to homogeneous isotropic jump because of the background space-time. But there are anisotropies. Of course, on small scale, we all know that when you look out in the sky, distinct objects are there. So clearly, there are inhomogeneities and anisotropies at a small scale. But large scale, at least, is supposed to be that. But even on large scale, it turns out that there are anisotropies and minor inhomogeneities. Now, CMB observations which are done, which actually show that these anisotropies exist. So when Kobe results came around, I think 89, 90, around that time, before that there are some indications that there is a dipole anisotropy or maybe quadruple anisotropy. That was in the 80s. Kobe was the one which first displayed that they measured the cosmic microwave background radiation and actually found that angular distribution has up to L equal to 30 mode anisotropy is there. L refers to the YLM theta phi. So that will be used to characterize how the deviation from spherical nature or isotropy is. So up to L equal to 30, you can see that means up to some angular scale, you'll see that temperatures are not the same. So there is a variation in that. Beyond, of course, now we go up to in Planck, we have gone up to about 2500 L. So at a much smaller angular scale, you can see the anisotropy. So this anisotropy is confirmed. Yeah.
Sir, are you using slides? The slides, if you are using them, they are not visible.
Oh.
Yes, it is visible. It's fine. The slides are
Fine.
fine.
Oh, sorry. Then it must be some technical problem here. Sorry, sir.
That's okay.
Sorry, sir.
No.
Maybe some technical problem here. Okay, sir.
Yeah. Okay. So this anisotropy is now the one can ask the question: why this anisotropy is there? Now you can imagine yourself in a suppose the screen that you see has vertical bands, and some of them are bright and some of them are dark.
No, wait. Sorry, Professor Shyam. Now, what we see is a slide titled Cosmological Anisotropies.
Yeah, correct. That's where I am.
Okay, fine.
Yeah. I'm just explaining some parts. I am the correct slide. That's correct. So now I'm just trying to relate what is the inhomogeneity, how does it reflect into anisotropies. So imagine that you are in this screen and there are vertical bands, which some of them are bright and some of them are dark. Okay. Now draw a circle from the center, draw a circle around it. Then you'll see on the circumference of that, there will be some portions, some arc lengths are bright, some arc lengths are dark. So the underlying inhomogeneous bands which are there, the distribution of bright and dark bands which are there, will be visible as angular distribution on the circle. Correct? Now, depending upon what is the size of this bands, you are going to get the angular distribution to be, some will be smaller, some will be larger, and so on. So in other words, the anisotropy that you see, which is what we see in the sky, which is like seeing the bands on the circumference, is actually a reflection of the inhomogeneities from which you are projecting it. Is that point clear? So now the question is why? So the existence of anisotropy means there are inhomogeneities. Why are inhomogeneities there? You have a three-dimensional space. So why is it? Why the temperature is inhomogeneous? The assumption is that it is because there are some perturbations taking place which you are not taken into account. So that's a dynamical process which is there. The origin for that is another separate issue to be handled. But let's say the perturbations are there, then they are going to cause inhomogeneities, and therefore they will reflect into anisotropies. So the experimental confirmation of anisotropies can be then considered as implying existence of perturbations, okay, which are there. Now, what are the noteworthy properties of this? There are many, of course, but I'm just going to focus on a couple of them. Namely, so if you take the average of the temperature that you see in the CMB, That average is denoted as T bar, and ask the question, how much is the temperature variation as you go from different angles? So the maximum size of that ratio is about 10 power minus 5. So it's 1 part in 10 power 5 that you are seeing this variation of anisotropy. And as for the normalization introduced by Kobe, the power spectrum, which is summarizing this angular distributions, is in this particular form. It has an amplitude part. This part is taken to be independent of time. So this is power spectrum at the time of decoupling. This amplitude is about 10 power minus 9, and this is for so-called scalar amplitude. I will describe briefly later. And tensor is what will correspond to the gravitational waves. That is about 0.03 of the scalar amplitude. The point is that the size of the, so what are the features of this perturbation? They are going to be having some length scale, like wavelengths. I can do the Fourier expansion, which I will do in a minute. I will have some length scale and also have some amplitude. The fact that the temperature anisotropy is 1 part in 10 power minus 5 says that the amplitude of these perturbations cannot be much larger. So that is small. How small is small? We characterize it in terms of this power spectrum, which I indicated earlier. And that amplitude is about 10 power minus. This is dimensionless. It's 10 power minus 9. So it's again very, very small, but this is estimated from the observation. How well are we finding out the angular distribution resolution? So after how many degrees or minutes, arc minutes, are you going to see that there is a variation in delta t? That resolution at Planck is about 10 arc minutes. So at the surface of last scattering, 10 arc minutes will correspond to about 30 megaparsec. This is a simple calculation. 180 degrees, that is antipodal points will correspond to about 36 gigaparsec, whereas current Hubble radius is about 4 gigaparsec. So which means there are going to be some, so remember this means that if I see the fluctuation which is correlating between antipodal points, then the corresponding wavelength of the inhomogeneous thing is about 36 GPS, which is way beyond the Hubble horizon. And there are some which are 30 megaparsec, which are much smaller than that, which means I'm going to get the spectrum of perturbations, their wavelengths, which are some of which are larger than the Hubble radius and some which are smaller than Hubble. This is something which will be important in a minute. Just a couple of slides, we'll see that. Just note it at moment. Now, this is fine. This is something that's seen only in Kobe. But of course, once the perturbations possibility is admitted, why do they have to be restricted only to this? They can be anywhere. They can from 0 to infinity. The wavelengths can go arbitrarily large, arbitrarily small. So if that is the case, how do we detect it? Well, we have to have different methods. CMB cannot do all of it, but there will be different methods. So here is the different experiments and their sensitivities to which frequency band I can detect, corresponding wavelength, and what kind of experiments. So ground-based interferometers, which are like LIGO type and so on, they are sensitive to variation up to about 1 kilohertz. 1 to 1 kilohertz, which is correspond to about 300 to 303 lakh kilometer wavelength range. Okay. Now, this will, of course, this is true even if the perturbations are generated primordially. But of course, we'll see that they are completely negligible when it comes to the nearby binary mergers. So what LIGO-based thing will detect, ground-based interferometer is not the background hum, but only the sources which are there. Space-based interferometer will have the frequency range of 10 power minus 5 to 0.1 hertz, or wavelengths up to about 10 power 10 kilometers. Pulsar timing arrays, I will talk about it a little later, just briefly. They go up to nano hertz frequency to 10 power minus 6, and the length scale will be up to 30 light years. That is the wavelength that we have. Whereas CMB, by contrast, goes from 10 power minus 19 to minus 18, which is way too frequency is very small, and the length scales are GPC, because these are the GPC that you see. So this is the length scale at which is visible in CMB. Other length scales are not visible in CMB. Pulsar timing arrays will see these length scales. Space-based LISA type experiments will show this, and this is the ground-based one. So this is the range in which one can probe what kind of gravitational waves could be there. Okay. So now let's look at closer look at what are the gravitational waves, how they are computed. So again, I will be very brief here. So again, we do at GPU is background metric plus little bit, and the corresponding stress tensor again background stress tensor plus little bit. Now it turns out that because you have general coordinates, that is the essential feature of general relativity. Not all HB news or TB news are physically distinct. It could be simply because I changed my coordinates and I changed from G bar mu to some new G. So, but this H mu is coming because of coordinate transformation, nothing to do with what is happening physically. What are those kinds of H mu? H mu which are of this type, where Xi mu is a vector field, are of those kinds which are coming only from general coordinate transformation. And likewise for the P1 mu, which correspond to so-called d derivatives of this, are again something which are not physical, the effect of changing the coordinates. But of course, I can change coordinates at will. Therefore, I must say that those two different H's which differ by this are to be identified as same quantities. So they are physical. So these are gauge transformations, and like in electromagnetism, you have the A mu and A prime mu, which is A mu plus del mu of some lambda. They are regarded as the same because the corresponding electric field is the same. Electromagnetic field is the same. So there are gauge invariant quantities and which are gauge variant quantities. So these guys are gauge variant, they depend upon gauges, and we have to either do completely gauge invariant variables you have to choose, or you have to say I fix the gauge and proceed with that. Both are used in practice. We'll do the fixing of gauge. So what does fixing of gauge means? We can say that my coordinates must satisfy certain conditions. Once that happens, I am no longer allowed to change them. So therefore, these things are gone. So whatever I do in this fixed coordinate system is my physical quantity. So those are so-called transverse stressless gauges and so on. Technical details apart, I can regard the physical H mu with the gravitational perturbations as those which satisfy this equation Hij's only. Hij's have the property that the divergence is zero and they're traceless. This part I forgot to write here. Yeah. And the trace is equal to zero, but these are only special coordinates. I don't need the other component. That is the result of the gauge fixing. Fine. Now, this is the bar is chosen to be the background metric. And for us, background metric is, of course, FRW metric. The special part of that is S squared and delta I, which is what we wrote in the beginning. Now, what are the solutions of this? Well, because they are spatially homogeneous, I can do the Fourier modes, and this is the Fourier transform that I do. These are two indices, so I get indices which correspond to the polarization of gravitational waves. Remember, just as electromagnetic waves have the E and B, which are vectors, or the corresponding potential is 4 vector. Likewise, we have the H mu here. There are two indices corresponding as this, and then corresponding polarization, which is again two indices. And there are two types. This is the property that follows from these conditions. They are denoted as plus and cross. Never mind the details. There are two types of such waves. They are all functions of k, but they are transverse. So this must hold. So it depends upon what this E is, depends upon what k is. So you fix the direction of k, and this E's must lie in the plane perpendicular to that. And they are again traceless, which follow from here. So this is the kind of expansion that one can do. Okay? This is general solution that we get for these waves. Fine. Just to simplify equations, you do some simple scaling, take out some parts, etc. And new quantity which are scaled from the scale factor, now using a variable eta, which I mentioned earlier. Again, the details are not so important, just the structure of that is sufficient. Double derivative with respect to eta, and this factor times h is equal to 0, the part which is there is 0. Now, what kind of A's do we have? This is true for any background that is any A of t that you choose. Okay. Now, the A of eta or A of t or A of eta happens to be of the form eta to the power alpha, where alpha is an integer. And that alpha is equal to 2 for matter dominated, alpha is equal to 1 for radiation dominated, and alpha equal to -1 for the exponential expansion. So three cases that we consider matter dominated, radiation dominated, and exponential expansion correspond to 3 different values of alphas, and the scale factor always changes in that fashion. From that, it's very easy to calculate a double prime by A, double derivative with respect to eta is simply given by this, and this is always positive for these 3 cases. Okay. Now, why am I saying that? Because this factor, whether this quantity is positive or negative, change the behavior of what the solution is. If this is positive, then the solution will be oscillatory. If this is negative, solution will be hyperbolic. So there will be growing mode and decaying mode, or there will be oscillating mode. That depends upon the sign of this. Sign of this is important. This is positive. This quantity is also positive. Therefore, it's going to divide the k square into those k square which are larger than this and those which are smaller than this. And that's exactly what this is. And they are known as this quantity is less than this correspond to, so this is same as 1 over eta, h is equal to eta inverse. So this just says that, and any physical wavelength is multiplied by the co-moving times a square, a, this will say that these modes which satisfy this condition related to this are super Hubble, these are sub Hubble. Now, again, I'm saying this not just to impress that there are these things, but they are very, depending upon the solutions have different properties. And those properties will reflect into saying how are which modes are going to be relevant in any given observation. And it is for that this part is. Okay, fine. So, super Hubble modes have the property that they will remain constant. So when you go back to these equations and look at what happens, we'll say oscillatory solution, the amplitude will not change. So these original H's which are there, they will remain constant. Whereas sub-Hubble will always decay as this. That means their amplitudes are going to get smaller and smaller as you evolve in time. Now, during accelerated phase, the mod eta decreases, and therefore, if at the beginning of exponential expansion, suppose some mode is super Hubble, it will remain so throughout, as long as the expansion continues. If it is sub-Hubble, it can become super Hubble. But if it is deceleration, then sub-Hubble remains sub-Hubble. So once that's sub-Hubble, then it will remain sub-Hubble forever. And that means this will keep falling off continuously. Whereas if it's super Hubble, the evolution will not change the amplitude. So amplitude is preserved here. That is the implication of the fact that you have the structure of the equations. Okay. Now, just to give an explicit example of this, again, don't have to pay attention to every single factor there. This is just a way of saying that the solution that I wrote here, HIJ, etc., this part, this is explicitly written in terms of something which depends upon the K and something which is functional upon the eta. Just solve. This is now second order ordinary differential equation. This one, this here, for example, double derivative, this equation in eta. And that solution for that, if I take it to be explicitly exponential expansion, then the solution happens to be of this part. Again, there's a reason why I'm mentioning that. So there is a normalization factor for this, which I keep 3. And this part is completely determined. The time dependence of this eta dependence is completely determined. Now comes the question, if these are generated primordially, then these are the initial conditions for this, right? You have second order differential equation, solution is given as some initial conditions, like the harmonic oscillator, you have Q0 and P0, or Q and Q dot. Likewise, these are the ones which are there for a given mode. These are two initial conditions which are there. I do not know anything about the initial condition. It could be randomly distributed. So I'll assume that their average is 0 and their 2-point function or 2-point correlation is proportional to K minus F with some amplitude, some AH. Okay? H for the remaining that is coming for this gravitational perturbations. And now this assumption that initial conditions are distributed with these properties will imply that the gravitational perturbation correlation function will come in this form. It has a part which is coming from this as well as the part which is coming from the solution. Okay? With EK given explicitly by this. Now the delta that I introduced in the beginning, while talking about generic delta phi, will be get related to this, and this part which is independent of P is called the power spectrum. Okay, just to get the terminology. Okay, what is the point of all this? There is a time dependence here, and there is this, and the power spectrum therefore has three functions of K. The alpha K, which is coming from the normalization of, I will need another maybe not more than 10 minutes, maximum time, less than that. There are two independent functions. Then the normalization constant, which I do not know, and there is this AH, which I postulated. Again, I do not know what. Okay. So all I can do is I can infer for observation and say, okay, this is what it is. All I know is that now I have three possibilities. The perturbation that I thought can be just a stochastic function. I do not know how it has come. Maybe just some function. After all, I have a differential equation, I have a solution. These are some solutions, and the initial conditions are randomly distributed. It's purely classical stochastic function. In which case, the alpha and A are completely free. I have no way of determining them from the theory. Observationally, you will get some. Suppose I assume that this H sigma is a classical field. That tells us that the H with a X and this conjugate momentum satisfy a Poisson bracket. That fixes this alpha K has to be of this. A is free. Okay. So that is something, the advantage of saying that this is a classical field. If it is a quantum field, if I make that assumption, then even A is determined by whatever quantum state exists. Because the expectation, the average value that I get now will be given a trace of the state with respect to the 2-point, the operators which are A dagger operators. So the assumption about whether the perturbations are of classical nature, stochastic functions. We'll leave this thing free. If it's classical field, I will still get some determination. Quantum field, I have better determination. So that's the advantage, theoretical advantage. Now, if you choose a vacuum to be something called, once there is vacuum, or let's say the quantum theory said that the state at the beginning of the inflation part is vacuum state, then this expectation value turns out to be just 1, and then the power spectrum is simply given by this equation. For large enough, for the super Hubble case, where this is negligible, this is just a constant, and that is the scale in spectrum for super Hubble. This is what is observed experimentally with some running, etc. Which is because this is for de Sitter. If you encounter a slow roll inflation, then you get some modification. Again, the lesson from this is that perturbations can be there. They can be expanded as Fourier modes. Their amplitudes are unknown, are not knowable unless you put some further assumptions, depending upon whether they are classical, stochastic functions, or fields or quantum fields. You can get some predictability of it. Okay? And ultimately, the numbers have to be determined from observation. Fine. Okay, so much for the perturbations which can be coming from primordial, which is very early in this, prior to the inflation. I'll change the track and go to the last topic, namely on the 5 minutes and more than. So this is the background which could be coming because of sources, localized sources, which happen to be distributed everywhere. Okay. So what are the sources? So again, like pick some sources which are mergers of supermassive black holes or whatever, and they are going to produce this background. They are going to produce gravitational waves, and we already mentioned that it could be, in principle, they are arbitrary frequencies. Ones which are detectable in this so-called pulsar timing arrays are in the range of nanohertz. Now, what are these arrays? So first, there are pulsars which are rotating neutron stars. I'm not talking about binary pulsar, just single pulsar. Because they are rotating, I mean, the pulsars typically are magnetic fields, and they are not aligned with the axis. So magnetic field keeps rotating, and therefore it produces electromagnetic beaming at radio frequency. There are different types of pulsars. Those which are millisecond pulsars are relevant for us right now. They are very, very stable, and their change in the period because of intrinsic dynamics is up to 2 of 10 power minus 15. So we have to wait for so many periods before any small change can be detected. Okay. Now, these radio waves which are coming from pulsar, originating from there and coming to Earth, they are coming through the local environment of the pulsar, intergalactic, interstellar medium, as well as solar system neighborhood, Earth neighborhood, and so on. Every one of them, they are going to suffer some time delays. Okay. So I'm not going to be able to see the uniform frequency, which is highly stable. The pulses which are coming from pulsar, they are coming at tuck, 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 tuck like that. I'm not going to see, I'm going to see some variation in that. Some of them will be a little faster, some of them will be slow. That could be, for example, the distance between, because of Earth's rotation, changes a little bit as it goes around the sun. Pulsar is somewhere fixed, very far away. So relative distance changes, and therefore there will be slight delays involved. This is just an example. There are many delays which are all classified and measured and so on. So what you observe is the time of arrival of the pulses. That is all you have is instrument. You simply say, I time track it and say, tuck, 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 tuck. These are the times at which these pulses are come. Now you make some modeling about what kind of delays are possible and how much is the delay which can come from various sources. That modeling of known sources will give known time delays. Now compare the actual delays which are there, which you observed in your data. The difference between them is called the delays of the residual time. Now, this residual time delay could be for a variety of reasons, either because intrinsic variation in the pulsar rotation, or could be so other parts modeling that were missed, or could be gravitational waves background. If they are gravitational wave background, what kind of residual time delays they will produce? That is the question which is being asked. Okay, so how do we identify this? Yeah. Now, a pulsar at a sky location P. So I have a star here. I'm here. Pulsar is far away, and the gravitational wave is passing by. So focus on the particular pulsar. The pulsar is at some direction P hat, and gravitational wave passing is some Hij Tx. Okay, some wave is there. I can calculate because the metric is now the flat metric plus this little bit, because we are talking about pulsar. They are all within our galaxy. So we are at a near geometry, so we don't really need to worry about the time scales there. So the metric is going to be just delta plus this Hij. This Pi part is there, which is that this is term 1. Total time elapsed is therefore going to be this. This is in presence of gravitational wave. If gravitational wave is not there, this term will be absent. And I will just get some number L times C. So fractional change in the pulse period is therefore delta T by T is computed from the difference of this minus this is just going to be this. Okay. So it is related to the polarization of the gravitational waves, epsilon by direction of the pulsar, this is contacting to this, the amplitude of the gravitational wave, and the kinematical factors such as the direction of the gravitational waves and direction of the pulsar. This formula can be very simple calculation from here. Can check it easily. So here T is the time of arrival, T is the direction of the gravitational wave, and sigma is the polarization. Okay. Now this is for a single pulsar. We do it for multiple pulsars. We choose that's why it's called an array. We choose some 50 different pulsars distributed appropriately in the stand, which are accessible, which are known, their properties are known, etc. And you calculate this time delay, the correlation, average over this. Okay. AB run over this 50 pulsar that you choose. That calculation will be, of course, averaging of this Hs, which are related to the power spectrum. This is H will come, and these are factors which are known. There is also this factor of the polarization involved in that. So that goes into the averaging. And then you integrate over, because these pulsars are distributed. So you have to integrate over the gravitational wave K is not coming in one direction. It's coming from all over the direction, which is why it is considered background, right? So I have to integrate over that. That angular integration produces a certain function called Helling-Downs function, which is function of the angle between the two pulsars. So when I'm looking at pulsar A and pulsar B, the correlation between them is angle between them is cosine of gamma alpha beta PA dot PB. Then this function can be calculated, is given by this. And gamma is that gamma. Now, you look at this pulsar, look at these parts you already know, you observe them sufficiently long time to do the averaging and find out and see how it fits into this. That if it fits to this form, I will read off what this A is. Therefore, I will know what is the background strength of the gravitational waves that I have, A that I choose in the earlier part. So that is how I can measure and estimate if this object is above error non-zero, then I say I have detected the gravitational background of at this frequency range which is accessible to the pulsar. Okay, so I'm done. Here is the summary. So waves are messengers from processes taking place far away. That's all waves do that. Gravitational waves fill in when electromagnetic waves step aside because they cannot watch it. They do so in the form of chirps as background hum, and also leave imprints on polarization anisotropics, which I didn't talk about. That is too complicated to mention. So that's one more feature which is there. And this is the main lesson which is there. So having the new form of waves will give you more information and are different epochs and different types. For those who want to little further reading, there are some references. This is archive. This is Tasi lectures, very recent, very readable, short, and that has more references. Of course, there are books, but I am not giving you references to that. So these three references are those who would like to follow it up further. And I thank you for your attention. I have gone more than an hour and 20 minutes, but I'm willing to have more questions. And thank you.
Okay. Okay, thank you so much for this wonderful talk, Professor Shyam. It was an extended and comprehensive description of gravitational waves. And now I hope everybody I now know the motivation behind studying gravitational waves and all. Now we will take questions, and please feel free to ask. And if you are too shy to ask, you can write it down in the comment box.
Yes. You can also, I mean, some questions, if I cannot answer, you send me the email and a question, I will answer and write it back. No problem. Yeah, so please go ahead. I will now remove the full screen so that I can also see chat and such. Yeah.
Sir, I could not understand much about the gauge transformations, but I would like to study them. Out of academic curiosity, I have a question. See, actually, when it comes to electrodynamics, there are two types of gauge transformations: Lorentz transformation and Coulombian gauge transformation. One deals with the one is okay for Schrodinger equation, that is Coulombian gauge, whereas the other one It's not like that. And similarly, I see a point here that there are two types of gauge transformations with the gravitational waves treatment. One deals with quantum case and the other one deals with the classical case. Suppose I study that other Coulombian and Lorentz gauge transformations in terms of field tensor in electrodynamics. Will I find some similarities between the gauge transformation here? Because this is doing with the here the gauge transformation in the present cases with the tensor also.
Yes.
So when I do that with the field tensor in the electrodynamics case,
Yeah.
will I find some similarities? Anything that will let me study this somewhat easier?
So let me explain. I mean, I use the term gauge transformation that is not common use in literature, but technically they are really coordinate transformations. And because Einstein's equations, I mean Einstein's theory, he says that coordinates by themselves are unimportant. I can choose my set of coordinates, you can choose your set of coordinates, and describe the phenomenon that way. For example, gravitation. I use the mu indices and explain who is t and who is x. I choose one set of time coordinate and x coordinate. You choose another set of time coordinates. And there is some transformation between this so that we can communicate what I'm doing and what say that my t is related to your t in this fashion and my x is related to your x in that fashion. That's all. That will change the description of how we describe the wave, how I describe the wave and how you describe it. Right? Okay. But we are still talking about the same wave. The phenomenon is the same. We're simply describing in different fashion because we choose different set of coordinates. So when I say that, let me complete, then I will come back. So, so I now say that the differences in the description are because of coordinate transformation, then they are not real differences. Physically, nothing is changing. Remain the same. What kind of changes are those which can be understood as coordinate transformations? Those are the ones that I mentioned, which are these transformations here, which I call, they are coming from coordinate transformation, and they are called gauge transformation by analogy. Okay, this is not really gauge potential. But if I write, this is the difference between this is delta of this quantity that is inhomogeneous. It depends, doesn't depend upon h itself. H is 0, this doesn't vanish. Okay. Like delta mu, the electromagnetic potential. See, in electromagnetism, there is a Lorentz transformation or coordinate transformation. They don't change anything. They will just change it and you know exactly what they are. But the quantities they change are themselves unambiguous. Electric field, magnetic fields are not gauge dependent. Only when you introduce mu field to describe E and D, you get two different S can give you same E and D. So their gauge transformation refers to different choice of A's which will give me same E in any given Lorentz frame, and you change it, they will transform appropriately. So there is no change coming from that. Here, these are not gauge transformations. They are actually coordinate transformations, but they behave as though, I mean, the point of gauge here is to say that which changes are redundant, which changes are real. So delta mu, and when you say Lorentz gauge is fixed, that is like saying that I say that the mu's that I'm using, they satisfy the property that del mu is equal to 0 or A0 is equal to 0, Coulomb gauge also. Okay, so I specify. After I specify that, I am no longer allowed to make gauge transformation. Then whatever I calculate, I get my E and B and I'm done. Similarly, if you fix a particular quantity and say my H mu must satisfy some relation, and only those coordinates in which H mu satisfies this relation are my physical, then I'm done. So although the word gauge transform is used, it is in the spirit that there are different configurations which are not physically real. They are mathematically real. I don't know if I answered the question, but this is what it is.
I will understand it better with further reading. So thank you. I got something. Thank you.
Yeah.
That
okay.
Here is all depending on it's a kind of coordinate.
I mean, I can explain it in more detail. Of course, it's possible to do so. Coordinate transformation. Find out the difference. Transform G mu and the old G mu. The difference will exactly turn up.
Okay. And you have given me references to try to understand.
Those references may not give the details, but they will have references will give the details. Sure. They're in all books. So.
Okay. Thank you.
Sure.
Thank you.
Sure.
Okay, Professor Shyam, there is one question in the chat box. Are you able to see it?
No.
Lengthy one.
What is the question? Wait a second. Where is the chat box? It seems to be. Second. Chat box. Here is the chat. There are some 5 points. Okay. Oops, sorry, I didn't see the chat earlier because it was full screen. So I'm sorry.
No, that was okay. That was the initial part. Then
Oh.
it was all right.
Okay. Due to the diminishing the mass of the binary components and the redshift values, are we constraining the mass components of binaries? First, calculate the mass of distance from the strain data and the coordinate parameter. We find the redshift there even from mass components. In that case, constraining mass components will be a problem since Hubble's parameter is different in each individual method, which is not about this question of Rakesh, I'm afraid I don't have any useful answer, but I don't understand it well enough to give a clear answer. This is, I think, best addressed to people who do the actual data analysis and infer the values. I'm afraid I don't have, I can't say anything useful here.
Oh, okay.
I'm sorry.
Uh,
Due to difference in the masses, binary components, or the same one, same question. Oh, or direct message versus. Oh, okay. I'm sorry, Rakesh. This is something which depends on the very detailed analysis of how the individual masses are computed and so on. See, because there is a great deal of modeling involved in that. You make for certain mass parameters, we assume so. Given certain binary parameters, you will get certain waveform. Now the waveforms are to be the mass parameters are made into banks, so they are made into bins, so as to construct the so-called banks of these waveforms. Then those waveforms are matched with the data to infer it. So it is inferred very indirectly. And then once those parameter estimation is done, then comes the question of what is the H, etc. is going to go. So I do not know exactly how many details are going there. So I'm unable to answer the question. Perhaps the best person to ask is Ajit or KG Arun at CMI and Ajit at ICTS. They're the ones who can answer it appropriately. Yeah.
Okay, I have something to ask you. That I know you are interested in black hole thermodynamics as well. Okay. So what I want to ask you is that are there works relating these two aspects, gravitational waves and black hole thermodynamics, not just restricted to observational regime, theoretical as well?
Black hole thermodynamics typically refers to equilibrium cases. Okay. When one talks about thermodynamics in equilibrium, there is of course actual dynamical process wherein you will have a collapsing object which will form a black hole, which will settle down and do something, etc., etc. Now, in that dynamical process, there will be generation of gravitational waves. So those are also types of sources which can be there, but they will not be. They will be in the transient part of the thing. Whereas once the black hole thermodynamics refers to the equilibrium states which are reached. So let's say you form one collapsing object, it is collapsing and at the same time generating gravitational waves, etc., etc., and it will produce finally a black hole. Okay. Then that black hole will have some mass, the angular momentum, charge, and the standard 3 parameters which are there. And you ask the question that if I were to disturb it again and change these parameters, how are the new parameters related to old parameters? So that is what will be given by the black hole thermodynamics.
Okay.
So that will be the so in that endpoints of this processes, beginning process and the transient part is not visible in the black hole thermodynamics.
Yeah.
So that will not come directly. The transient part where the emission will be there. So if you do numerical simulation and actually track it, then of course you will see what is the how much gravitational waves emitted from there and what values are finally reached. That's what we will get in the simulation, certainly. Also, if your black hole is disturbed a little bit, then you get the so-called quasi-normal modes. Okay, yeah. So black hole will go back to itself. Again, that's a transient process. And that, of course, is something, a signal which is gravitational wave detection fellows are looking for that signal. So that will be clear signature of a black hole, especially the no air theorem and so on. But as such, directly they won't be related, because one is a transient phenomenon, which has to be necessarily, because waves don't generate it in the static situation. And other is the equilibrium properties, where they're essentially static. So they won't be directly related in that sense.
Okay. Okay, thank you.
You could have different kind of questions, meaning whether the gravitational waves themselves can collapse and things like that and form black holes. Those are very different kind of questions. I think
Okay.
Chandrasekhar had some work on this colliding gravitational waves, whether they can form black holes or not. That will be different kind of processes will form black holes. That's a very different kind of thing. One is here talking about the waves which are so-called weak gravitational waves, which are perturbations of some background.
Okay,
okay, thank you. So do we have
Yeah.
more questions?
Hi Shyam.
Yes,
Yeah, so I have a couple of questions.
Sure.
So first question is about, I mean, you mentioned the work of Bondi et al., right? Like, so I know that, so you have worked with Jahanur on something similar in cosmological spacetimes, and before that there was work by Ashtekar and
Sure.
people about, how to calculate flux of gravitational waves in cosmology. So can you comment on what is the current status of that work, in the sense, are questions settled, or like, yeah.
I did work after the first couple of papers on this topic in detail, because what we used was uh, the Isaacson tensor, which is what is used in also flat space Minkowski background. It works fine. Here we used in a limited sense, in limited quantity, because it cannot be used generally, because you don't have the short wavelength approximation validated. However, because our focus that time was to look at whether we can use the cosmological horizon as a place where we can track these fluxes. That was the idea that we had that. Subsequently, Janur has worked with various collaborators and so on, and I think there is one work which is with Samantha, Janur, and Oliveri, 2105, where they have talked about asymptotically digital spacetime, and they also talked about the fluxes and so on. But again, I do not know whether I can put it at this on par with Bondi et al.'s work, in the sense as complete and decisive, because there are some issues involved in what exactly is meant by asymptotically digital space. I'm not completely 100% sure that the issues settle fully. But there are certainly flux calculations are there. There is also mass loss formulas are there. So I think it will be fair to say that I can't say that it is completely settled, but that may be because my not being completely up to date on that. But some progress definitely is there, because these things have been, the fluxes formula, etc., have been calculated. So that is as much as I can say.
Okay. And my second question is
Well,
yeah, so you mentioned about these pulsar timing arrays and all, no? So you sort of briefly gave an overview of the theory. Can you comment on the observational aspect of that?
well, as far as I know, again, it's something that I heard a colloquium by Manjari Bakshi when this last year, 2023, the nanohertz wave detection was there. But I think they were at some level of 4 sigma or something. So they are not, they have to wait for more data to be able to see. So the problem is, again, I mean, I didn't talk about any of the details. There are many noise sources, etc. there. Plus, the data has to be accumulated over. We are talking about nanohertz, so that will correspond to see, 1 year is about 10 power 7 seconds. We are talking about 10 power 9. Okay, so 100 years data we don't have. Certainly, we are not going to do that. So it will be 1/10 of that also. So 10 years data is there. So more data comes, they will have more pulses. The millisecond means you'll have many more pulses and more statistics is available. So they are waiting for the statistics to see whether you can you see the correlation which is following this Hellingsdown's distribution, angular distribution. Once that is confirmed within the error bars and so on, then one can say, okay, they have been detected. But as far as I know from that colloquium, that they're still waiting for more data to be accumulated. So then they will be able to say, push the sigma level to 4.5 or 5 or so. So that is what I can say. That was
Okay,
general.
okay. Yeah, thanks, Shyam.
Sure.
Okay, so we are almost in 2 hours, and we can't be more thankful for being with us for a long time, and thanks a lot. And hopefully, we hope that we could contact you for our in near future programs for a school or to give a set of talks or something, right? Okay, so yeah.
Because I have to apologize a little bit because I knew it was 45 minutes, and my aim was to at least give some plausible arguments as to what the logical steps in between are. So it actually extended more than what I thought. I hope people have not got
It's,
too much
right.
load. I will have a write-up of this to some extent. Slides are there, but some rough notes of these are there. I can make it available. I'll probably put it or something. The write-up of the slides themselves, which will a little more expanded version of what I discussed.
Okay.
With some further reflections. I will do that in a few days.
Okay. Thank you.
Okay.
So we will be in touch then.
Yeah,
Thanks a
sure.
lot.
Sure. Most welcome. Okay.
Okay.